Washington. I'd like to welcome you all to the Kennedy Space Center and to the Mars Science Laboratory Curiosity Tweet-Up. This is the 31st NASA Tweet-Up and the 9th Launch Tweet-Up. For those of you joining us online, you can find out more information about how to connect with NASA and some background on the NASA Tweet-Ups at www.nasa.gov/connect. And of course, we'd invite you to follow along with the conversation here at twitter.com/NASA Tweet-Up. Now, we're joined by 150 tweeps from around the country and around the world here for a couple of days of programs and some behind-the-scenes tours. And we're going to cap it all off with a successful launch of MSL tomorrow on the Atlas V at 10:02 a.m. And you can watch along with us at nasa.gov/NTV. Now, we're here for the Mars Science Laboratory Curiosity rover. And this will be by far the most complex robotic lander ever attempted, the largest thing that we have ever put on another planet. It is an absolute marvel of engineering and science investigation. And you're going to meet some of the voices and some of the people that helped put it together, that helped design it, that the idea came out of their head, and they're going to be here with us today, and we're really excited to have them. The rover and its 10 instruments are heading to Mars tomorrow for an 8.5-month trip to Gale Crater, which is a perfect environment if you want to investigate the past or present habitability. Now, our first speaker, Dr. Jim Green, runs the NASA Planetary Division. NASA science breaks down into 4 divisions: heliophysics, study of our sun; earth science; planetary, everything inside the solar system other than those 2 bodies; and astrophysics, everything outside the solar system. So Jim, as director of the Planetary Division, leads one of the oldest scientific pursuits, I think, in the world, and that's the observation and discovery of the solar system's planetary objects. And that means tackling some of the biggest questions, like how did our solar system develop, and how did life get here, and could it have developed elsewhere? It's actually really exciting to have Jim here. It'll be his first Tweet-Up. But also, working at NASA, you get your mind blown all the time just in hallway conversations and sitting in people's offices, and he's one of the ones that do it to me every time. He's both patient with my dumb questions and incredibly passionate, so I can go into Jim's office and I go, what's up with Titan? And he goes, oh man, it's raining methane. You have no idea how exciting this is, and he begins to explain it, and you just walk away absolutely enthused, and his energy is infectious. So it's really exciting to have him here. Again, it's his first Tweet-Up, so please make him feel welcome, and I'll turn it over to Dr. Jim Green.
Thank you very much. Indeed, this is my first Tweet-Up, so I'm going to tell you what I think about planetary science. I'm as a planetary scientist, I have a very unique view. Planetary science was invented by NASA. Okay? What we did before NASA was astronomy. All right? That means you sat at a telescope and you looked at the solar system and you watched the wandering planets as they moved, and you speculated or you made a series of observations and determined their orbits, etc. But when NASA came into being, it changed everything. It changed that field from astronomy to geology, magnetospheric physics, atmospheric physics, because we go there and we discover new things each and every time. Well, this has just been an unbelievable year for planetary science, and in fact, we call it the year of the solar system. It's 670 days. That's right. It's a Mars year. And we're right in the middle of it. What's happened over the last 300 days has been 2 comet flybys. Back to Tempel 1, where we looked at that comet after it went by the sun and looked at the impact region, that deep impact hit, and saw how a comet changes as it makes its perihelion pass. The second comet, Hartley 2. Hartley 2 is a small comet, but it was packed full of surprises. We saw that comet snow All right? It was literally falling apart. Most comets, as they come in, the heat from the sun, the light from the sun, heats up the surface, changes from solid right into vapor. We call that sublimation. But what was happening on Hartley 2? Geysers of material were flying out. Things as big as golf balls all the way to volleyballs were flying out of Hartley 2. Not only on the sunlit side, but on the night side. Rewrote the textbooks right away. We thought we knew something about cometary science. We found out we had a lot more to learn. We had 2 orbit insertions. We inserted Mercury, a messenger in orbit around Mercury. That was hard to do, went flawlessly. We're now studying that object like we've never seen it before. We have a suite of instruments on it, from magnetospheric measurements that look at the variation in the magnetic field as the solar wind hits it. We see emissions of sodium coming out of the pole, going down the magnetotail of Mercury and out into the solar wind. We're charting the altimetry of every place on Mercury, looking for volcanic activity in the cratering record. It's a fascinating planet. Why? It is so unusual. It's bigger than the moon, okay, but smaller than Mars. Its core is bigger than that of the Earth's. Okay? It is one of the more densest planets from a terrestrial perspective than we've seen, rivaling only Earth and Venus. So what crushed it? Or how much iron does it have? We don't see the iron on the surface. It's mostly silicates. Wow, what a new planet that has been. And we just got in orbit. We got in orbit around an asteroid called Vesta with Dawn. Okay. Yeah, that's a good one. There's a number of Dawn people there. And it is a new dawn because what we know about the asteroid belt, the 300,000 or more objects that exist between the orbit of Mars and Jupiter, is that in reality, that material is trying to become a planet. So when we go to Dawn, we're going back in time and look at the early evolution of terrestrial planets in our solar system. Jupiter, and its massive size, is what's keeping these objects apart. And Vesta is one of the largest ones. It's about 500 kilometers in diameter. It has huge mountain in the southern hemisphere. It's about 15 kilometers. That's twice the size of Mount Everest on a body only 300 miles in diameter. Unbelievable. Unbelievable. Then, at this place, we launched Juno to Jupiter. Yeah, fabulous mission. It's going to Jupiter, it's going to orbit Jupiter, and it's going to determine, by looking at the composition of Jupiter as deep into the atmosphere as it possibly can, what the composition of the early collapsing cloud was. So we get an idea of what we started with. That's very important. And we also, from this site, we launched Grail, 2 spacecraft in September. And they're on their way to the moon. And they're not there yet. They're taking their time. They're lollygagging around. Okay? And like every planetary major milestone, we're going to insert them in orbit on a holiday. Absolutely. What else can we do? One gets into orbit on the 31st of December. 26 hours later, we stick the second one on January 1st. We're going to be up anyway. So what a fabulous set of missions and activities. And of course, the capstone in the year of the solar system is going to happen starting tomorrow with the launch of MSL. And in that next 9 months, we'll find that landing. We'll find that landing spot, and we will stick it right in the landing ellipse. It's exactly what we're going to do. And then along in the way, we'll be done looking at Vesta, and Dawn will break orbit and go on to Ceres. Another fabulous, fabulous opportunity for us to learn something else about the biggest asteroid in the asteroid belt. So with that, hopefully that leaves some time for questions.
Any questions?
There's one behind you.
I'd just like to take you to say that you do a fantastic job, and I do a lot of outreach back in Ireland using NASA images, in particular Cassini-Saturn images, with children to do with drawing, learning through drawing. So I just love to have those images and really appreciate being here. That's all I really want to say. Thanks very much.
Oh, my pleasure. And although I didn't talk about Cassini, I mean, we've got several other spacecraft that are in orbit and operating. Cassini is a fabulous flagship. It is making observations, scanning, using its radar, the surface of Titan. And as Trent said earlier, we have found lakes on Titan, lakes of methane and ethane, hundreds of them. We're also watching as the seasons go by, and yes, there's season in the outer solar system just like there are here. We're watching the lakes evaporate, and we're watching lakes grow in the southern hemisphere. It is right now raining methane on Titan, and that is true. That's unbelievable. It's absolutely unbelievable. What about Titan? Titan is huge. It's huge. It's much bigger than the moon, and in fact, it is bigger than the planet Mercury. If you were to pull it out of the Saturn system, put it around the sun, we'd call that a planet. Next question.
Is it true that Opportunity will be able to see MSL actually enter Martian atmosphere?
Opportunity? Ooh, that's a good question. I don't think so, but ask the guy that follows me. See, Doug is already checking it out. He's tweeting himself. You better get that one right. Now, I'd love to say that we would observe MSL coming in just like we did with Mars Reconnaissance Orbiter for Phoenix. I don't know if that'll happen, but Doug might know. Doug does know. That's the guy to ask. Okay.
So when are we aiming for Mars sample return?
Okay, Mars sample return. Why do we need samples? Well, we need samples because that's a gift that keeps on giving. We're still analyzing the lunar samples. What we're finding out from the lunar material has already changed our view of the origin and evolution of the solar system. So let me take 1 minute and tell you how. When we brought back 800 pounds of rocks and regolith from the Apollos and started to date those rocks, we got a surprise. We assumed all the rocks would have an early age for which, as that body was created at 4 billion years ago plus, that's what the age of these rocks would be. It turns out we were wrong. We see the age of the rocks at 4 billion years, but then at about 3.8 billion years, we see a whole series of rocks with that age. We didn't know what that was. It had to have been a bombardment period. That material had to come in and hit the moon because the moon was already created. So we called that period the late heavy bombardment. And then we looked at other things. We see from the biological record on Earth, life began about 3.8 billion years ago. Is that a coincidence? Might be. Anything that bombards the moon, and the record of our history of the bombardment of the solar system is laying on the surface of the moon, bombarded the Earth. It bombarded Mars. It bombarded Venus, and it bombarded Mercury. All right? So that's a fundamental process that happens. So what is it? Well, several years ago, doing computer modeling, it was recognized, well, let's model something for which the planets, where they are right now, will change their position and see what happens. And when they did that, they found that the planets moved. They adjusted themselves. Gravitational resonances and interactions from the planets have pushed them around. And when we recognized that became unbelievable. And so then the computer modelers really went to work to understand that more. And we have now a pretty good model. It looks like as Jupiter was forming and it was moving inward, it ended up with a gravitational resonance for Saturn, pushed Saturn out, it pushed Uranus and Neptune out, and it brought the Kuiper belt in. And in that modeling, that occurred at about 3.8 billion years ago. Okay? So that means the late heavy bombardment, which fits completely independently, might be because material debris in the outer part of the solar system made up of ices, water ice, ammonia ice, other kinds of ices, came in and bombarded the Earth, Mars, Mercury, Venus. Maybe brought the key ingredients to life. And in fact, some of the planetary physicists believe that anywhere from 30 to 60% of the water that's currently on this planet came from the late heavy bombardment. Okay? And that's just from lunar samples. And we keep getting more and more information from those. So, indeed, bringing back samples from Mars will change our perspective of how the solar system emerged and evolved, for sure, and for many, many years. Yes?
Hi, for my students back in the Bronx, 4th and 5th graders, what do you think the most significant planet outside of Earth is, in personal opinion? What fascinates you? What captures your interest?
Wow. Okay. Wow. Okay, confession time. So this is like an AA meeting. I mean, I'm the Planetary Science Division Director. I mean, I gotta love everything. All right, everything. All right. But if I had to say there's one special spot, I'd have to go back to my field. I'm a magnetospheric physicist. And there is a moon. It's around Jupiter that has a magnetic field. It generates its own magnetic field. It is so bizarre, it's unbelievable. It's called Ganymede. It's also the largest moon in our solar system. What is that about? So to me, that's fascinating. Let's find out more about Ganymede. Of course, that's at Jupiter, and we're trying to develop some missions in our future. The Planetary Science Decadal, this is the scientists got together and say the things that we want to do. We want to go to Europa, and when we go to Europa, we're certainly going to fly by Ganymede. So in our future, we'll discover those things. But as I said, everything in the solar system has its own fascination. It really does. Yes?
Okay, I'm a Mars person. I love Mars, but I do have a question. Are we ever going to send a mission out to Neptune?
Are we ever going to send another mission out to Neptune? Well, I would like to think in my lifetime we could do that. Neptune and Uranus are, in many ways, very different from Saturn and Jupiter. We call those ice giants, okay? So in the planetary decadal, where our scientists have gotten together to say, these are the top questions that we need to answer, one of them is, we got to go to Uranus. We got to see what these ice giants are all about. And the only reason they picked Uranus above Neptune is in this next decade, the alignment of the planets are such that that's the easier one to get to. But in the decade after this, Neptune ends up being a little easier. So I would like to think that we could do that. And when we do, it won't be a flyby. It'll be an orbiter. What you may not realize is we have a particular process that we use as we chart out things in the solar system. The first is flyby. We do our reconnaissance missions. The next is from that we gain the information that we need to make the prioritization and the selection to go and orbit. And then we want to land, we want to rove, and we want to bring back samples. And for Mars, that's where we're at. We're down with MSL, and the next ones we want to do in this decade, indeed, will have sample return. So Neptune will be an orbiter. That's our next shot on that one. Yes, sir.
You talked about Europa. How far along are plans for that mission? And are you planning on drilling into the subsurface ocean, potential subsurface ocean?
Very good question. Europa, just to remind everybody, is one of those special moons of Jupiter. Okay? And in the planetary decadal, it is very high in the priority ordering. We've been studying Europa for a long time. It is really tough to get to because of its environment. It's in the very hefty radiation belt environment of Jupiter. And so if we get into orbit, we've got to have, something bigger than a Sherman tank. Something that will literally last enough time for us to be able to probe, do our radar scans, and find out how thick that ice. So if you want to go under the ice, you got to pick the place. To pick the place, you got to, at least from orbit, determine where those places are, where the water is closest to the surface. And so the orbiter is probably the next best idea on Europa, and that's the tough one we're working on. Right now, it's in the study phase.
So if
Yes,
I know the search for life is something everyone's interested in. If you had the unlimited budget to build one probe and send it to either Mars, one of Jupiter's icy moons, or Titan to look for life, which would you choose and why?
Okay, my bet's on Mars. My bet's on Mars. For several reasons. We know more about Mars than any of the others. I think we can pick the right place. It's got to be a step that we have to take before we bring humans there. I mean, everything about it is such that it's got to be Mars. In addition to that, I got a steak dinner bet on that, by the way. and that's from my deputy, Jim Adams. He's going to lose. I'm bound and determined to make sure he loses that bet. But let's talk a little bit about finding life. One of the things that we do also in planetary science is we invest in analogs here on Earth. That means we go to places that look like extremes in the solar system, and we run and operate a variety of experiments. That turns out to be very important. It enables us to plan for those experiments to be on landers and rovers, and enables us also to work with astronauts who would accompany many of these robotic systems. But when we go to these analogs and when we study life, we see in the extreme areas here on Earth, you're going down in the Atlantic where the Atlantic ridge is, where the plates are moving, and it's extremely hot, and the pressures are really high. It's teeming with life. You can go to these ice shelves in the Antarctic, and you get right underneath them. The interface between water and ice, there's life. All right? So it's, to me, by studying Earth and the extremes at Earth and finding life everywhere we look, the analogies that are out in the solar system, if life exists anywhere off this Earth, then it is everywhere. And we're on the road to find that. So who's got the mic? Okay, we got one over here.
Hi, I have a question from one of my Twitter followers, and he wants to know if there will be any more attempts to contact Spirit.
That's another one Doug can answer, but there's been so much effort in doing that that I don't believe it'll wake up. It didn't survive the winter. Spirit and Opportunity have to winter. They have to find a place where they can roll up and put their solar panels such that as the sun is low on the horizon, it can get as much power as possible. And it couldn't do that out of the sand trap that it was in. And electronic equipment only survives so well in extreme temperatures, and it suffered that. But there are things going on, and Doug can give you a little bit more on that.
And that's our last question for your talk.
What?
Yeah, sorry.
I just got here. All right. Thank you very much.
Flew by, right? right, who says smart can't be cool? Am I right? You see what I'm talking about? Don't you want to go sit in his office for like 10 minutes over lunch? Man, oh man, oh man. Come visit us at headquarters. Okay, our next speaker is Doug McQuistion. Say this. One day when astronauts are walking on Mars and we're all watching it together in 3D or plasma or whatever's next, think back on this day, but particularly what you're about to hear from the next person, because there's a strategy involved in Martian exploration that's incredibly sophisticated and complex and successful, and they do these amazing things. And Doug runs the NASA Mars Exploration Program. So throughout his career, I mean, he's been working in different capacities at NASA in earth science and in space science and at the Goddard Space Flight Center and the U.S. Navy. But as program director now for Mars exploration, he's leading that strategy behind all the missions that are helping us really grapple with the mysteries of this red planet. It has polar ice caps and clouds and an atmosphere and seasonal weather patterns and volcanoes and canyons and other things that we recognize here on Earth, but under very different conditions. So if you want to answer those big questions about Mars, was there life there? Was it ever living? Is there anything there now? You have to build on what you've learned so far from rovers and other missions, and then you look forward to what MSL will do and what will Curiosity find? And that's the big question, and Doug's grappling with it. And let's introduce him, and please help me give a big welcome to Doug McQuistion.
Okay. So first, thanks for having me. This is also, just like Jim said, my first tweet up, so please be gentle with me. But I'd like to thank you guys all for spending your Thanksgiving down here in Florida with us. And especially for our international colleagues. We have international folks so hopefully you got turkey and you kind of participated a little bit in American Thanksgiving. So that's great. Everybody see the rollout this morning? No? Yes? No? All right. Well, it was amazing. It was one of those, you got to get out of the way. That thing moves so fast. Once it comes out of the vertical integration facility, it is trucking. They had three train engines on it, and it was cruising up that hill. So that was pretty exciting. MSL, the monster truck of Mars, right? So this is, it's amazing. Every time I look at it, I am astounded by what we have done. I really think that we are actually finally accomplishing science fiction. 2,000 pounds, small car with a trunkload of instruments. It's an exciting piece of equipment. So a lot of questions about Spirit and Opportunity here, so let me hit a couple of those right up front. Opportunity is still doing well. Opportunity's arrays are kind of dirty. So in the winter coming, Mars goes through the same seasons like Jim was talking about other planets and things do. And we have a hard winter coming. The obliquity of the planet, the angles, the elliptical orbit makes some winters harder than others, and the one coming is going to be tough. So we'll see how Opportunity does for it. We'll park it appropriately. I doubt that we'll try talking to Spirit again. There may be an opportunity to, no pun intended there, sorry. we may be able to once in a while, but there's nothing really in the plan. We pulled every trick out of the book that we could, and I just don't think we're going to hear from Spirit again. It's unfortunate. But we've got MRO cranking at the planet. It's bringing images back that are unbelievable. If we get really lucky, hopefully we'll be able to get an image of MSL coming in. That was we set an expectation with getting that Phoenix image that we may never be able to live up to, but now everybody wants us to get another one, so we are certainly going to give it a try. Whether Opportunity can see it or not, while I could cheap out like Jim did and say, well, Ashwan will answer that question, I won't do that to Ashwan. I actually don't know the answer to that. So I've sent an email, thanks to you guys, whoever it was that asked that question. I sent an email back to the project manager, and I said, hey, have we looked at this yet? Because we should. Now, Opportunity is way across the planet from where MSL is going to land. So I'm not sure that it's going to work out. But it's worth looking at. It's worth thinking about. Might be able to see a bright spot in the sky as it gets closer or something. I don't know. We'll see. That's pretty cool. Odyssey's doing great. It's our bent pipe. It's going to be sending information back all the way to the surface with MSL as it goes through the atmosphere, our 6 minutes of terror. MRO is a store and forward. It'll be collecting all the data and then dumping it back to us when it's done. But those will give us some really, really good indications of how things are going with MSL. And of course, then we hit the ground softly and unfold and start moving. So those first images are going to be wild. I remember the first images from Phoenix when we saw those come up after landing. And I mean, everybody was hugging everybody, jumping up and down, yelling and screaming, and that was pretty cool. It was pretty cool. So looking forward to that with MSL. So back to the monster truck theme here. You guys have seen, right, our toaster oven, right? We flew Pathfinder many, many years ago. And then we moved to the coffee tables. So this is an MER wheel. You guys have probably all been playing with this week. I hope this is one of the metal ones, but it's probably plastic in there. Yeah, this is a plastic one, so I'm going to leave it there. The advance in technology here, talk about the engineering for a second. The advancement in technology from toaster ovens to small automobiles with a trunkload of instruments is astounding. We missed a launch opportunity. Hate to say that. It's the first one we've missed in 10 years. But we needed to do that. This was so hard. I don't think any of us realized how hard this was going to be when we started. But it is absolutely a feat of engineering, and it will bring science like nobody's ever expected. I can't even imagine the discoveries that we're going to come up with. I think it just continues to bring back into people's mind, yeah, I'm biased, I'll put my hand over this for a second, that Mars is still the coolest place in the solar system other than the Earth, right? So I think Jim's left. I think I was allowed to say that. But it is. I mean, and we're going to land in Gale Crater, down in the bottom of that, and the vistas are going to be amazing. Mount Whitney almost on one side of us, and then how high the walls of the crater are on the other side will be an amazing thing to see. So, I look at all these different landing sites we were looking at, and frankly, a Talking Heads song keeps coming to my mind about, take me to the river. And that's where we're going. That's where we're going. So, this is really a transitional mission, not just from an engineering perspective, right, as I talked about, but it's a transitional mission scientifically. So our understanding of water and the history of water on this planet has changed dramatically in the past 10 years. And it was a strategic intent to do that. From Odyssey, with the HEND instrumentation, and understanding how much hydrogen really is there, which potentially is water. In many cases it is. In most cases it probably is. To Spirit and Opportunity with everything from the blueberries that we found, the sedimentary layers that we spotted, and things like that. And then followed by MRO with the multispectral, actually hyperspectral CRISM instrument to understand what the composition of materials on the surface were in a way we've never, ever expected to do before. Finding phyllosilicates, finding sulfates. Understanding water around the planet. I imagine you guys have seen the briny water releases, right, where it's in the seasonally and regionally, it's coming down the sides of crater walls extensively for months and months, it looks like. That's just wild. A mission other than an MRO no other mission has ever been able to do anything like that. So our understanding of the role of water, which is obviously one of our key life ingredients on Mars, has just exploded. And MSL is that transitionary mission. And frankly, it's kind of interesting that it actually hits the 2 decades. So it's kind of in between the 2 decades. The first decade was following the water. And we followed it, we found it, we've actually smelled it and tasted it with Phoenix. We understand what we have. And now we transition to seeking the signs of life. We know we have energy, we know we have the food and nutrients, we know we have water, and we can prove all of those. So we move into seeking the signs of life. MSL, this is the legal disclaimer at the bottom of the print, right, is not a life-finding mission. But, we may find enough to really give ourselves a really solid idea of where to go to find past or present life. And that's what sample return's all about. We got a couple more cycles to go. MAVEN comes in 2013. That's going to give us an idea and a good understanding of what happened to the atmosphere. Where did it go and why? How long did it take for that to happen? A critical ingredient in understanding the past history and also feed into where we might go. And we have a partnership we're working with the Europeans, as you know, and hopefully what we'll get is a trace gas mission in 2016 that will help us understand the role of methane. Is that regional, seasonal methane there? How concentrated is it? And we're looking at instruments, actually I have some instruments under contract, that may be able to help us find where to locate the vents for that methane, to try to understand where it's coming from. Obviously an ingredient. You only get methane 2 ways, right? Geologically and biologically. With the constituent trace gases around methane, maybe we can figure out which one it is, but at least give us some interesting ideas on where to go. And then after that, we hope, per the decadal survey, to start a Mars sample return mission in 2018 and actually go collect the samples, figure out how to do that, and prepare to bring them back 10 years, 20 years later or something, at least get the ball rolling. So pretty exciting future for this program, too. Pretty exciting future for all of you guys in the room, too, hopefully. We'll keep doing this. So I had no prepared remarks, so I'm just rambling. So I will stop and open it for questions.
Okay.
I had a quick question on the rover and the whole sky crane situation. It blows my mind watching that. Every time I see the video that you guys put together, that falling out, hypersonic speeds, and just kicks that thing out, and then gradually settles down. I mean, what kind of testing, land testing, or any that has been done, and what's your confidence behind that?
Actually, this is the one area that cannot be tested on Earth end to end. You can test the rover end to end. You can test, the heat shield end to end because you can use arc jets and things. EDL you can't, and there's so many activities that occur from the top of the atmosphere to putting it on the ground, and every one of them has to go right. That is pretty scary, which is why we call it the 6 minutes of terror. So we test the pieces. We've tested the sky crane itself, and the engines have all been tested extremely thoroughly. The umbilical devices have been tested thoroughly. We actually drop engineering models of the rover in a tower out of JPL. We drop the thing on rocks and on sand dunes and all kinds of stuff to see how those big honking wheels actually perform, and the rocker bogies as well. The software gets run through test beds. We run it and run it and run it. In fact, as soon as we launch, we will start what we call robustness testing, where we try to break the software. Right? So we've tested the hardware enough that we know the hardware works. Software really kind of ties it all together. So we're going to try to break it. We're going to, at a minimum, test the corners of the envelope of where its performance limits are. So the testing has been extensive. It really has. That's one thing the 2-year slip did for us, is we put a lot more energy into testing than we'd had time to do before. My confidence level, I'm scared to death of any entry and landing. I really am. So it's hard to hold your breath for 6 minutes. It's really tough. I did it on Phoenix, so I guess I can do it again. But my confidence level is very high. This team is spectacular. The guys and the gals working this are just incredible. So, another question? Yeah.
Hi, thanks for coming to talk to us today and sharing all this great info. Even though Curiosity will be far away from Opportunity, is there any chance or anticipation that they may collaborate? So will Curiosity maybe find something or gather some information that we might want to double check with Opportunity, or vice versa?
That's an interesting question. I'll give you my thoughts. Ashwan Vasveda, who's the deputy project scientist, I think comes after me, so he can probably do a better job of this. The instrumentation on MERs, we got 5 kilograms of instruments, right? We got like 80 kilograms of instruments on MSL. So we may find things on and the other piece is Opportunity is a very interesting location now, right, at Endeavour Crater. And there's some things there that we've never seen before by Spirit or by Opportunity. So there may be some things that Curiosity finds that we can then utilize through the ops team of different ways to use the MER instruments, maybe different ways to understand what we're looking at or look at things a little bit differently. So I think there could be some scientific collaboration there. Yeah, it could be very interesting. Maybe vice versa, but I think MSL with the higher capabilities better. Yeah. Yes?
So I had a question. What lessons did we learn from the previous rovers that informed the engineering that went into MSL? I know wheels got stuck and tools got blunted, so I was just curious about that.
Yeah, there's some good examples of that. Drill bits is probably one of the first. There was no drill on MER, but there's a rat, right? It's a grinding tool. And we wore those out. We basically just wore them down to nothing. We have spare drill bits on MSL right on the front of the rover, so we can take a drill bit, put it back in the bit box, grab a new drill bit. So I think we've got 2. So we have a total of 3. 1 we're going to land with and 2 more. That's one. A lot of software actually has been developed during the long life of Spirit and Opportunity that's translated to MSL. The ability to drive around, recognize hazards and drive around them, plot a path to go around them. ways to understand what sand dunes are really composed of and whether we can go over them or sometimes try to go through them, not so successfully. So there's a lot of interchange there. Just rover technology itself, how wheels work, how motors work, how long they last, how you treat them, and the fact that once they break, it doesn't necessarily mean you're dead in the water, right, or dead in the sand. So I'd love to be dead in the water. That'd be great on Mars. So if we have a wheel that's broken, we've been dragging wheels with Spirit, and we got one a little off-center with Opportunity. So we've learned a lot of operational stuff too. Next one.
With the success of prior missions as far as deployment and landing on Mars, what caused you guys to move away from what's worked in the past and go with the type of landing we're going to have with Curiosity?
Oh, man, that's a great question. And it's actually reasonably simple. It's called mass. So we were pushing the edge of the envelope with Spirit and Opportunity and airbags. And it's 175 kilograms is what an MER rover weighs. And we're at 900 kilograms even on this guy. You can't get that kind of mass down with airbags. You can't do it. So you're looking at either a Viking technique, engines underneath, kind of Phoenix-ish, and land it that way, or you can take them and kind of flip them upside down and put the engines on the top. So there's a couple of advantages there. You don't want to drive around with the engines and prop tanks hanging on your rover. So put them on something you can get rid of. And the other is we're not going to get the sky crane all that close to the ground, so you're not going to disturb things nearly as badly as Viking did, and you're not going to contaminate things as badly with the hydrogen gas exhaust, right? So those were the drivers. Mass was the real key, though. Mass was the key.
Hi. As we continue to explore Mars and do research both here on Earth and in Mars, what studies, programs, or degrees would you consider telling the children out there to look at as they prepare to do different things for NASA?
Yeah, that's a great question. There are so many, it's tough. I don't know where to start. If you're interested in science, I think you need, geology is good. I think Jim mentioned that. My degrees are biochemistry, biology, and that's the science of the future. If you're looking for life, biochemistry is a great way to go. On the engineering side, though, it's not quite as easy because we have everybody from high school graduates to PhDs in engineering working on the hardware. So the technicians, highly skilled technicians, some don't even have a college degree, are down on the floor working on building, testing, assembling, rebuilding and things, the mechanical elements of this mission. So you don't have to have a college degree to do some of these things. If you want to get into the design of this thing and some of the more intricate detail work, mechanical engineering is great if that turns you on. Software engineering is unbelievably sophisticated now. I mean, the software on this thing is incredible. So the software engineers are employed more than they've ever been, I think, on past landed missions anyway. So that's great. And electronics. I don't know if you've seen a picture of the inside of this rover, but it's almost solid. That whole chassis is almost solid in electronic boxes. So boy, the double E's have really had a heyday in there. So I think there's almost any opportunity you want. Really is. Long way to go.
Okay, last one.
Yeah, last one. Okay.
Hi, it's my understanding that the landing ellipse that MSL is going to be going into is considerably smaller than some of the previous missions. Can you comment on kind of the key innovations that went into the lander that enable us to be able to shrink that landing ellipse to its size?
Yeah, absolutely. So the landing ellipse on the airbag-based missions tend to run something on the order of 50 kilometers wide and 100 to 150 kilometers long. It's a big ellipse. And it's actually not the bouncing of the airbag, which when I took this job, that's what I thought it was that caused that problem. But it's actually not. It was a ballistic entry. So you're not really guiding the entry. That's the big difference on MSL, is we're actually controlling the vehicle all the way through the atmosphere. So we have ballast masts that are in the aeroshell that we eject to change angle of attack. We're controlling the angle of attack of the vehicle in there, so it's actually a lifting body. So we come in and we actually drive for a while and control it before we then put it down. So the technology is completely different. And that's really what shrank it to the 20-kilometer circle. We think we can get that circle smaller in the future. We think we can get it down to maybe 5 to 7 kilometers, maybe 10, something on that order, with a little better guidance and a thing called hazard detection and terrain avoidance, where kind of like cruise missiles actually look at the ground and they have a map on board and they say, this is where I am. So then you actually would be able to steer it once it's in a sky crane mode to get to where how far are you going to go, 100 yards, 200 yards. But you can go to areas with big rocks and stuff for a change, which is one of our killers, right? And say, oh, there's a huge boulder. Let's move, 50 feet this way to land. So that could be the next generation development. Okay. Thanks again for having me. This was fun. Appreciate it.
Doug McQuistion, everybody. Thanks a lot, Doug. If you've been watching this landing animation, I mean, you'd go see that movie, right? But no, there are people at JPL that are going to do that in real life, and it's mind-blowing, but you're going to meet a few of them. So I'm actually going to hand the microphone over to my colleague from JPL, Stephanie Smith, who's going to introduce you to a few of our colleagues at JPL.
Thanks, Trent. So it is my supreme honor to introduce two of my colleagues from JPL who were instrumental in the engineering of the Curiosity Mars rover and the Mars Science Laboratory mission. First up, we've got Bettina Pavri, who has worked on MSL since 2008, shepherding the mechanical and electrical integration and functional test of all the instruments. As those 10 science instruments rolled into JPL from our partners around the country and around the globe, she and her team made sure that they played nice with each other, they played nice with the rover's power system, its communications, every part of that gorgeous machine. And also, Al Chen. Al's the flight dynamics lead. He was responsible for making sure that we would land what we said we would land, where we said we would land it. And you've seen the animation. Is there a guy with a more stressful job out there? He's also the operations lead for getting the spacecraft ready to execute that entry, descent, and landing sequence. And he's also newly on Twitter. His handle, I can call you Betty, and you can call him Al. Al Chen and Bettina Pavri, everybody.
Thank you all so much for being here and getting the word out about MSL. We really appreciate you getting everyone excited about our mission because we're really excited about it ourselves. So just briefly a little bit about what I do. I appreciate the nice introduction. Part of what we need to do is we need to bring these instruments from all over the world. We have contributions from Canada, from France, from Germany, from Russia, from Spain, and all over the U.S., and bring those people together who have built those science instruments. They've been working on them for years, getting them working as individual units, and then bring them to JPL and integrate them with the rover. So we have the electronics team and the mechanical team at JPL who've been building the rover, and we bring those instruments here, and then we say we need to make sure that they are going to fit mechanically, that they're going to be protected from vibration. So that's one big part of our job. And so the previous speaker was mentioning the inside of the rover is packed full of electronics. Just to emphasize it even further, it's not just packed full, it's an intricate three-dimensional puzzle to try to fit all of those pieces in there together. So we have to very carefully make sure that we can fit everything in and that we assemble it in the right order such that we can get all those pieces in. So we work with the people at JPL and the instrument teams to accomplish that. Then we have to electrically integrate all of these things together. So that means that we're checking signal compatibility and integrity to make sure that those science instruments, many of which have are very, very delicate and very, very precise. We need to make sure those electrical interfaces work well together. And then finally, we need to make sure that these instruments function as part of the rover system. So we have system level tests where we test all of the instruments together. We drive the rover while operating the instruments. We use the communication systems. We operate the mechanisms. And then we can determine, are there things we can't use together? Are the things that we need to make sure don't conflict with one another? So those are the kinds of things that we do together. So now we're working with the science team in order to plan our first days on Mars. And we'll be working throughout cruise to make sure that we are ready to go when we land. So at that point, I'll hand it off to Alan Chen to tell you a little bit about what he does, and then we'll take questions from you. Thank you.
As Stephanie mentioned, I'm on the EDL team, and I've been on MSL since 2002. So thought about this the other day. I've been working for about 10 years by the time we land to get about 7 minutes to go right. But I've seen this mission on a lot of different phases from the beginning all the way through now, hopefully operations here, and been excited the whole way. It's been many different types of rovers. It's been 400 kilos, it's been 600 kilos, it's been 900 kilos, and we finally settled out at 900. But it's been a blast working on it, and excited to answer any questions you guys have. So just take them right away.
With respect to the integration side of things, I work in the aerospace industry, so what kind of busing do you guys use to communicate with the different tester instruments, everything like that on the robot?
Yes, so some of the science instruments are LVDS protocol, and some are high-speed serial. So it depends what makes sense for that particular instrument.
Hi, I actually have a question from one of my second graders who tweeted me and wanted me to ask, how long did it take to actually put the rover together?
So the assembly really started back in 2007. So, but you have to realize before that, all of the pieces were already being built, and so pieces were sort of coming together at all different levels. But the real, what we call ATLO, assembly, test, launch operations, that whole process really started in 2007.
I remember seeing the first slabs of the descent stage, the giant pieces of aluminum that are the kind of the core. That was in 2005, 2006, before we sent those off to be machined. So it takes a while.
Hi. How long do you hope to get information coming back from the rover?
Right. The Prime mission is 1 Mars year, so it's about 2 Earth years. Hopefully it'll last much longer than that, but what we're designing to is that 1 Mars year of life.
Hi, thanks for the work that you're doing. I work with a lot of amateur robotics groups, including some high school first teams. Are there resources, lessons learned, techniques, plans even, software that's available that you guys have worked out that those teams and those groups can use to kind of replicate some of the work that you're doing, or perhaps use that as a leg up for the projects that they're working on?
I think the biggest resource actually that we have is a number of us are actually working on FIRST robotics teams with those students. But so there's a lot of folks you can draw on. Certainly, the things that we learn about this are entered in NASA's Lessons Learned database, which I don't know if it's available to the world, but certainly those things get out, can get published fairly frequently. I'm not sure what would be necessarily directly applicable to FIRST robotics students, but there's certainly some basic lessons that we learn and often relearn going through this. So we can definitely hook you up with some information about that later if you'd like.
Hi, I'm Jeff Handy from St. Petersburg. I wanted to know what you do to keep dust from gumming up the works.
So for the science instruments, we have several calibration targets, for example, that we actually place magnets in them to help keep the dust away, because the dust, that will help essentially attract the dust away from the areas that we care about seeing. When we land, actually the cameras either have covers, or the ones that are, those are the body-mounted cameras, and then the ones that are up on the mast is stowed against the body of the rover with a little lip around it to keep dirt from getting inside. So a lot of thought has gone into both modeling that dust plume and also understanding how we're going to protect all of the science instruments to make sure that that they're not going to be covered with dust when we want to get started.
For EDL, we mostly just go quick. Get down quick, land safely, don't worry about it, and hopefully it won't screw up the weather.
Another question from students. They get so attached to the rovers when they see the animations, and it's for my 9 and 10-year-olds, it's beyond their comprehension that you're going to leave that amazing machine on another planet. And so they want to know, how do you all feel about it when you've put your life's energy into this and knowing that it's not coming home?
Well, I'm kind of hoping that maybe some of your students can go visit it. And another way to think about it is in about 4.5 billion years, when the sun swells up and maybe consumes the Earth, MSL will still be there on Mars, and it'll still be a record of what we put there. So I'd like to think of it as a good thing.
On the previous Mars missions, the stopping points seemed to come related to power, and they were solar powered. Now that this one is nuclear powered, seems like that's less likely of a possibility. What are the expected points of failure that would bring the mission to a close?
So one of the things that the team is doing right now is we have a version of the rover which is located at JPL. We call it the Vehicle System Testbed, the VSTB, and it looks almost exactly like the real rover. And we operate it all the time, 3 shifts a day. And one of the things we want to do is to understand how the rover will break down. And if it breaks down, how can we work around that? How can we prevent that from happening? So we are operating all the parts of the rover just to try to figure out that issue. My suspicion is that if anything breaks down, it's probably at some point going to be mechanisms in a manner similar to the MER rovers, right? Wheels are going to start getting tired, mechanisms aren't going to work as well anymore, it's going to take more and more current to drive them, things like that. But with our MER experience, we plan to figure out how we can operate the rover as long as possible and get as much science as we can.
Last question over here.
Sure. With the EDL as complicated as it is, are there ways you can have a failure in one part of that sequence and continue on to Mars? What kind of contingencies are built into the EDL?
Yeah, I'm confident this is going to work, but we've got a lot of things that have to go right to make it happen. There's very little that we can survive if a failure happens during EDL. That being said, there are certainly places that are more graceful than others while we're hanging on the chute. If something goes wrong there, we're probably still in decent shape. However, we're counting on this thing to work right the first time and everything to work right the first time we use it.
Any other questions?
Yeah, we'll do one more.
I was kind of wondering, you have like this 100-watt power supply coming from the nuclear device. How many different voltages are all these systems using?
So in general, it's a 28-volt balance bus. So that's the typical power system that's going out to all the instruments and the different subsystems.
Okay, let's have a big round of applause.
Thank you.
All right, everybody. Up next, we've got Ryan Bechtel. He's the Power Systems Safety Manager from the Department of Energy. Yeah. It's a round of applause for the Department of Energy. Department of Energy has been NASA's partner for a long and storied career of providing power sources like the MMRTG, the multi-mission radioisotope thermoelectric generator, which is going to both heat and power the Mars Curiosity rover. So Ryan will tell you more about that power source, about the history, and for visuals for his presentation, if you'd like to follow along, on that online resources page at jpl.nasa.gov/MSLinfo. It's the first PDF on the page. So take it away, Ryan. Paper is so passé, we've actually got his presentation right here for him. So there are your cheat sheets.
All right, thank you.
Enjoy.
Hi, everyone. Thank you for having me here. I'm Ryan Bechtel from the U.S. Department of Energy, and I'm here to tell you about the multi-mission radioisotope thermoelectric generator, or MMRTG for short, because the other one takes way too long to say. So this is the latest incarnation of our nuclear power systems. It's based on the legacy of the previous RTG, which operated on Mars for the Viking missions. It also has all the built-in safety systems which we used for the last 30 years on the GPHS RTG. And I'll get to talking about some of those later. Over the last 50 years, we've had over 26 missions which have used radioisotope power systems. They've explored every planet in the solar system except for Mercury. We've done flybys of Venus 3 times, Uranus and Neptune each once, and in 2015, the New Horizons spacecraft powered by an RTG will make a pass past Pluto. And hopefully it might encounter a few other objects further out inside the Kuiper Belt. We also have other kinds of nuclear power sources on other spacecraft which have gone out there. Spirit and Opportunity, which have been mentioned a few times earlier today, they have our tiny radioisotope heater units, and they just supply a little bit of heat to help keep all the vital components warm during the cold Martian nights and winters. The MMRTG, in this case, it actually supplies both heat and electricity to the rover to keep all the components warm and run all the instruments on the rover. The device itself, and we have a half-scale model right here. That's the MMRTG. The real one is twice that size. It's about 2 feet long and 2 feet tall. It produces 110 watts of electricity at launch. When we measured the wattage, I think it was about a week and a half ago, we exceeded that. We're at 113 watts. The generator itself is designed for a 14-year lifetime. This is the most ambitious and longest lifetime or engineering design lifetime of any of our RTGs. However, over the last 50 years, all of our RTGs have far exceeded their built lifetime. For instance, the RTGs which were on the Voyager spacecraft launched in 1977 and still operating today over 11 billion miles from Earth only had a design lifetime of 5 years. We fully expect those power systems to provide enough power to keep the Voyager missions going past their 50th anniversary. So what you have here, there's the cutout of the MMRTG, and you'll have this in the PDFs, which I believe all of you had received. At the very middle of it are these orange blocks called the general purpose heat source. And I have a cutout of one right here. Unfortunately, it might not be easy for everyone to see in the back. But this is the actual size of the GPHS module. And we built safety from the inside out and the outside in into all aspects of the GPHS module. And I'll get to that in a little bit. Surrounding the GPHS blocks are all of our thermocouples. There are over 400 thermocouples on the MMRTG. And thermocouples, if you're not familiar with them, they're very common in industrial applications. What they're used for is to determine the temperature of something. Chances are you have several in your house. Does anybody here have an electric thermometer, kind you would put under your tongue? At the very tip of that, that's a thermocouple. We just use much thicker thermocouples, and they operate at slightly different, far higher temperatures. So out from there, then there's the housing of the unit, and that's just there to help radiate off the heat and keep everything together. So at the middle of our source is the plutonium fuel itself. And this is the actual size of the plutonium fuel pellets which we use. It's about the size of a marshmallow. And there are 32 of these inside the power system. At the center of the pellet, or the fuel clad, which is what we call it, represented by this red material here, that's the plutonium-238 dioxide. And we choose plutonium-238 because it's an alpha emitter, and alpha particles are very easy to shield. They can be stopped by a single sheet of paper. They can even be stopped by the dead skin on your body. Additionally, because it's in an oxide form, it's a ceramic material, so that if you hit it, it will break into large, non-respirable sized pieces. It's also insoluble, so that if you somehow ingested it, it would be quickly passed through your body and removed the same way that everything else gets removed. Surrounding the pellet is an iridium cladding. Unfortunately, I don't have any iridium to show you today, but it's very, very dense. It's the second densest element in the universe. If you had a piece of iridium about the size of a cookie, that would weigh over 2 pounds. So I've handled it. It's more than you think it would be. But we use that because it's a very strong and ductile material. It bends but does not break. And we've done safety tests to show this. And we have fired it out of a pneumatic cannon into steel and concrete walls. And obviously those are surrounded by very thick material. But that's the actual plutonium pellets. And we've done this at speeds as far as 220 meters per second. And we had no release in that case. So the iridium cladding, just consulting my notes a little bit more, has a high melting point. It's over 2,400 degrees Celsius. That's more than enough to protect it from a lot of the fires which we would expect. It's also corrosion resistant. It can last in seawater. And it's compatible with all the other materials which you would find in the general purpose heat source module. So what we do is we take 2 fuel clads and we put them inside something called a graphite impact shell. It's about the size of a salt shaker, and everything I'm showing you today, these are the actual sizes. It's just plastic and metal, so nothing radioactive. And this is made out of a material called fine weave pierced fabric. It's a reentry material, and it's also a very strong carbon-carbon material. So in the unlikely event of a reentry accident, it would survive to hit the ground. It also acts like the bumper on your car, where it absorbs the impact and prevents that energy from being transferred into the fuel clad. Surrounding that is what we call a carbon-bonded carbon fiber sleeve. It's an insulator sleeve, also made out of carbon, and that's to protect the fuel from the heat of reentry and from the heat of fires that might be found in the unlikely event of a launch area accident. And then 2 of these are then placed inside the module itself. Again, this is the actual size. And then these are stacked one on top of another inside the RTG. Now, we've done a series of safety testing on all of these. We've built over 30 years of safety testing and analysis into all of our power systems. We've done explosive overpressure tests where we've placed the GPHS module inside an explosive chamber, blew it up. We still couldn't get a release of material. We've impacted them with titanium and aluminum bullets. It dents the cladding, but we don't get any releases. We've done some aerodynamic property tests on it. We've burned them in solid propellant fires. And as again, I've brought up that we would impact the clads themselves. We also impact the entire module to show that the material would still be contained in some of the. Actually, it's more. We over-test all of them. We hit them at a much higher velocity than they could possibly achieve here on Earth. About 20 years ago, we built large-scale or full-scale RTGs and impacted them on rocket sleds, just to show that we could still better understand the behavior of the full system during an accident. And we use those tests today to factor into our computer models. So, does anybody have any questions? Yes?
Microphone's coming over.
Oh, okay.
Navigating a sea of tweeps. Hang on. Where was it?
I was just curious where the plutonium came from. I thought I remembered that there was no production of it anymore in the United States. Is that incorrect?
The U.S. stopped producing plutonium-238 back in 1988. The fuel which we're using for the MMRTG for Curiosity, that actually came from Russia. We've since purchased that material. And this is the first time that we're using an RTG entirely fueled by Russian plutonium. Another question here?
You've obviously put a lot of work into the safety of these materials and their housings and all of that. Is there any thing that you've learned that is going to go into commercial uses of this here on Earth for nuclear power plants or other uses?
This isn't an efficient power system. We just take the commercial nuclear power plants. Those use fission in order to generate the heat. In this case, we just take the natural decay heat of plutonium-238, all the kinetic energy that comes in with the alpha particles, and we use that in order to generate electricity. So these generate a lot less power. We're only talking about 110 watts. So depending on what kind of light bulbs you use, it's anywhere from 1 to 4 light bulbs. Nuclear power plants on the order of 1,000 megawatts or 500 megawatts and above. So it's a very different system here. One of the things that we do, some of the applicability of this is the understanding the fuel form, the plutonium dioxide, that can be applied to some mixed oxide fuel reactors, which is both uranium and plutonium, to better understand how that fuel would behave.
So you're producing 113 watts of electricity. How many watts of equivalent heat are you producing that can be used to keep the rover warm?
I'm trying to recall the number, sorry. We have roughly a 2 kilowatt heat load, 2,000 watts. Of that, roughly 5 to 6% becomes the electricity. Let me get back to you. I'm sorry. I don't know how many watts we deliver in heat, but it's enough to keep all the systems warm and comfortable on the Martian surface.
Question here in the back.
Hello, I'm Arma358 on Twitter. How is the public being informed and protected by the information that's being released by DOE with the launch of this RTG?
Are you asking about how we get the information out there?
Yes.
Okay. We have the fact sheets which have gone out. Those are available in both the DOE and the NASA websites. The websites, just for my program at DOE, we can have all that information up there. The overall safety of the power systems can be found in the environmental impact statement for MSL. If you type MSL EIS, I'm sure it'll be the first page that comes up, and you can find out about all that information there. And that's compliant with with NEPA, the National Environmental Protection Act. Additionally, we've done several other press outreach events earlier this year. A few of us, myself included, went out to the Brevard County Fair to help educate people about both the rover and the nuclear power system. And we've done some various press events over the last couple months to help educate the local press about the mission and the power system.
Back here to your right again.
Where am I?
Sorry, go ahead.
You mentioned using the generators to heat the equipment on the rover. How is the heat transferred from the generator into the main body of the rover?
Okay. See if there's... All right, we actually don't have that. Surrounding on the outsides of the MMRTG around that cylinder are actually Freon loops. So Freon takes the heat from the outside of the cylindrical part of the MMRTG, and that gets cycled into the rover.
Okay, back here to your right.
Oh.
So right now it's 110 watts. What are the minimum power requirements by MSL, and how fast is it going to get there?
I actually don't know what the minimum power requirements are for the rover. Generally, the decay, it's about 1% per year going down, and we have a minimum of a 14-year lifetime. So we're looking at probably about 90 to 96 watts after about 14 years.
Any final questions? Yeah. Here in the background.
I'm just wondering about the relationship between the Department of Energy and NASA on developing this. Did you guys create it, or do you work together? Do scientists design this, or how does that work?
It's constrained by the Atomic Energy Act, so this winds up becoming a DOE project, but it's entirely funded by NASA, and that's just the way that Congress has it set up. The actual design was done by one of our contractors, Pratt & Whitney Rocketdyne, with Teledyne Energy Systems contributing to that, and then our 4 national labs helped with the actual construction, assembly, and testing of the power system. Those labs are Los Alamos National Lab, Sandia National Laboratories, Oak Ridge National Lab, and the Idaho National Lab. And one last one right here.
It's quite cold on Mars, but it's even colder during the flights. What's going to keep the rover warm during flight? Is that also the RTG, or is there something else in?
Yeah, during the flight, we actually have to remove heat from the aeroshell because you've got 2,000 watts of heat, and if we didn't have a way of removing that heat, it could cause things to overheat because all that heat's trapped inside. So the heat is pumped around. It keeps the rover warm while it's in the aeroshell, and it's also sent out to radiators on the outside of the spacecraft, which radiates it out into space.
Okay, let's give it up for Ryan Bechtel, everybody. Thank you for joining us.
All right. Who's ready for some science? Yeah? Science! Well, we have some scientific heavy hitters here for you. We have Ashwin Visavada, who is the deputy project scientist for the entire MSL mission. He is one of my colleagues at JPL, And with him, we have Pan Conrad, formerly of JPL, now of NASA's Goddard Space Flight Center. She is an astrobiologist who has traveled to the ends of the Earth looking for life. She has been on six Antarctic expeditions, 7 Antarctic expeditions, and 1 submersible voyage to hydrothermal vents. Yeah, they're cool. All right, so bring it on up. Oh, one more thing about, come on up. Ashwin plays drums. Pan is a classically trained vocalist. There has been talk of an MSL band. What do you guys think? Should they get a band? They don't have a name yet, so maybe we could crowdsource that for them. You can tweet suggestions, hashtag MSL band. All right. Ashwin, take it away.
All right, thanks.
You want a band?
Here you go. We'll be here all week. Thank you. No.
Enjoy the buffet.
Yeah, right. All right, well, it is awesome to be here. What's up, everybody? We're going to blind you with science for the next 15 minutes. We have an incredible rover. You know, this is really a dream thing for scientists who've been involved with Mars exploration. It's the biggest and most capable scientific explorer we've ever sent to the surface of another planet. We're setting records all over the place. The size of our science team is one of them. We have over 200 scientists from around the world, which part of our job is to corral them into making decisions every day of what to do with the rover, like herding cats. But so that gets fun next August. But until then, one thing I want to tell you is that we have a fantastic landing site, and I hope you appreciate how cool a place Gale Crater is. Gale Crater is about 100 miles across, and right in the smack in the middle of the crater, there is a 3-mile-high mountain. And that mountain of rock did not form with the crater. It formed sometime after as material blowing around or being driven around by water on early Mars created all these rock layers in the middle of Gale Crater. And then it was stripped back to where just the central mountain remains. Y'all been to the Grand Canyon? Yeah, so it's very similar to that, or other places around Earth where you could study ancient history of Earth by looking layer by layer at the rocks. So we're going to Gale Crater, and we're going to do some mountain climbing with this rover where we start with the lowest, oldest rock layers and work our way up to progressively later in Mars history. And going layer by layer, we can do the main goal of this mission, which is to search for habitable environments where any of those time periods in early Mars history, time periods that could have supported microbial life. That's the goal of Curiosity. We don't really detect life per se. We set the stage for that life detection by figuring out which time periods in early Mars history were the most likely to have supported life and even preserved evidence of that for us today. So really briefly, I'm just going to whiz through some of the incredible instruments we have. We have the capability to survey the surroundings better than any previous rover with 2 color HD cameras, a medium and a telephoto lens. We have a ChemCam, this great instrument that zaps rocks with a laser from up to 20 feet away, and then we look at the color of the spark that's created, tells us what the rocks are made out of. So just by driving around, looking around, and shooting with our laser, we can figure out what's around us. If we find something interesting, we'll deploy this 200-pound robotic arm with all these tools on the end of it. One of those tools is a magnifying glass camera. We can look at rocks up close with that. Another one is another chemical analyzer. We can look element by element what the rocks and soils are made out of. While this is all going on, we have a weather station. We haven't sent a full weather station to Mars in a long time. We do pressure, humidity, temperature. We'll have weather reports so you guys can help us get that word out. And then we'll have a radiation detector that's actually flown by the human program, the astronaut program for NASA, is sending a radiation detector on this rover to figure out what environments astronauts will have to put up with when they go to Mars someday. So there's just a ton going on, and the real novel capability of this rover is the ability to sample rocks and analyze them on board with laboratories that we bring with us. You know, we've brought virtual geologists to Mars before. What we have never done before is bring the laboratories with them. And that's what we're doing with Curiosity, and that's what my colleague Pan's going to tell you about.
So in this very capable suite of instruments are 2 buried in the belly of the rover. We call this the analytical suite. One of them is for doing definitive mineralogy, and the way we do definitive mineralogy on Earth is with X-ray powder diffraction. So we have our X-ray powder diffractometer. It's called ChemIn. And next to ChemIn in the belly of the rover is the center of my universe. It's called Sample Analysis at Mars. It's a suite of mass spectrometers, and we're going to measure Martian chemistry, both from the gases that we evolve from solid samples, and also we can directly inhale the Martian atmosphere. So with this powerful suite of analytical instruments, what we hope to do is be able to not only contribute to our information about the present potential habitability of the Martian surface, but also get a look at the past. And the way we get a look at the past is the same way we do it on Earth, and that is we go into the rock record. So one reason why I'm very excited about Gale Crater is because it has the thickest package of sediments that we can find on Mars, and it gives us the opportunity to go deep into time, see what we can see in the Martian rock record. Now, that presents a couple of challenges. First of all, we have to put the signatures of a habitable environment into the Martian rock record, and then second, we have to preserve those signatures. So all the agents of attack against the Earth rock record, well, we know what those are on Earth. We don't know the full suite of agents of attack on the Martian rock record. On Earth, it's primarily water and our friends, or that is the other biology that eat away at the evidence through time. On Mars, we don't know whether there's ever been a biosphere. We think that there's been water activity on Mars, but there's also been radiation. But one thing we know for certain is that at a moment in time, Mars lost its protective magnetic field, and so there have been more cosmic rays and more solar energetic particles attacking the rock record on Mars. So it'll be a real interesting challenge to try to figure out what that initial evidence of habitability might have been, and what it used to look like when it was put in there, and what it now looks like. So as we begin this extraterrestrial real estate assessment, we've got to be open to all possibilities. We have to, and I say this a lot, so you'll probably get tired of seeing this in my own tweets tomorrow, we got to divorce ourselves from Earth. We got to think Mars, we can't think Earth. Of course, we've got to take our basis of our understanding about habitability from what we do know on Earth, and then try and spin the air around in our head and figure out what that might look like on Mars.
And with that, we'll take questions for whatever time we have left.
Question? Lauren? Okay.
You want this one or that one?
So, Pam, how do you do that?
With difficulty and lots of forethought. So that's actually a very good question, and it's not trivial to answer. On Earth, we've been following the water, and in space, we've been following the water. But one thing we know for certain is that life needs more stuff than just water. So in order to understand the full suite of requirements for habitability, we have to think broadly. The way I do it on Earth when I go into the field is I measure everything that I can, probably about a dozen parameters: how much water there is, what the inventory of chemical elements might be, what the redox environment is, as typified not by something like the pH of water, but by the suite of minerals that are collected together. I look at the isotopic ratios, and we're going to do that on Mars with Sam. I look at all kinds of things about the radiation environment. We're going to do that on Mars with RAD. There are so many things that we don't know about habitability that I advocate measuring all of it and then looking for trends. On Earth, we can do that easily. We can associate the presence or diversity of life with a certain collection of characteristics. We hope what we will be able to do on Mars is look at trends of things that cluster together and then try to make an educated guess about what they might portend.
I also have a question. Like, we see these images where you see rocks like on Earth they would look like water flowed over it. But what makes you think that was actually water? It was not like some other substance, liquid hydrogen or something like that. Why do you think that was water?
Well, I'll take a shot and then let Ashwin take a shot. So actually there are lots of signatures of water. First of all, certain kinds of minerals precipitate in water. Other kinds of minerals actually have water embedded in it, or they have OH, or just hydroxyl, as part of the mineral. We also see textures and structures that are associated with deposition underwater or with the action of water on the rock. So I think you've all seen the photos of different types of cross-bedding and sedimentary structures from Spirit and Opportunity. And so we look for those kinds of sedimentary structures as further evidence of water activity.
I think that's what I would have said. Water is just one of the more abundant elements in the universe and on Mars, and so it's just the more likely candidate. And we know it's liquid at the temperatures that Mars is and probably has been at for some time. CO2 is another option, but it just seems more what's the word? Hard to imagine, than water, especially when you have water buried in the ice caps and below the surface.
Over here to your right. To your right.
How soon after the rover lands do you expect to start getting some data to analyze?
Yeah, great question. So we've been actually planning the first week on Mars in the last few months, which is really exciting because you work on this thing so long, and then all of a sudden it's really real when you start putting the first week together. We land at about 10 o'clock at night JPL time, and then with both orbiters, MRO and Odyssey, overhead collecting data from the landing. One of those orbiters, an hour or so later, comes back on a secondary pass and is able to take about 3 megabits of data from the rover. So that'll be the first chance to get some actual images. We hope we'll be able to send a front and rear HazCam image. These are those cameras that help us drive. Pretty wide angle, black and white images. And if we're really lucky, one color picture from the magnifying glass camera that's still going to be in its undeployed state connected to the front of the rover, but it happens to be looking off to the side. So if things work out really well, as soon as the rover lands, it'll take some pictures front and back, take that MOLI image, the orbiter will come by, we'll get the data, and that would be awesome. We don't want to set expectations for everything going perfectly, but that would be the best case scenario.
All the way to your left.
So, Dr. Vasavada, you won't remember this, but way back in 2007, you gave me what you said was your first press interview about the Mars Science Laboratory. And the only reason I bring that up is that was a long time ago, and I know that for you and the team this has been a long, long road. And I just wanted to say I'm so excited for you and for all of us that tomorrow we're going back to Mars.
Awesome. Thank you so much.
And my other tweet asked my exact question I was going to ask, but I have another one, and that is, since this mission could potentially be on the surface for a long time, if everything goes well, what are some of the things you might be able to learn over the course of multiple Martian years, crossing our fingers that maybe there could be a mission extension, and what could you learn doing that?
Well, one thing we know from Earth science, from astrobiology, from geobiology, is that associated with a habitable environment is a certain level of dynamics. And one of the things we want to understand about Mars is how dynamic it is now relative to how dynamic it might have been in its past. And one of the things that we get to do is basically time-resolved experiments. So one in particular that I'm very excited about is because SAM directly inhales Martian atmosphere, we can look at what we see about the Martian air very close to the ground at rover height, and we can do it at different hours of the day, and we can do it on different days in different seasons. And that's a very important insight about the thermal environment, the solar environment, the radiation environment, and the chemical environment. And having a rover that can go during all seasons enables us to be able to ask those kinds of time-resolved questions. The other thing is, something that makes this very, very special relative to what the Viking lander started is, Viking could only process a couple of samples, but we can process many, many samples. So for as long as our bodies hold together on that rover, we can keep going, and the more samples we process, the better statistics we have, and the more we can make I wasn't going to say a more certain inference, but the better inferences we can make because we've got more experimental data. So my birthday was last Sunday. I just turned 59, and I'm hoping to retire on this mission.
Keep it going for Austin and Pam. Thanks very much for coming. One more big round of applause for our speakers. Thank you. Okay, so we've heard about the rover, we've heard about planetary science, we've heard about the engineering. We're here for launch, yes? Tomorrow? All right. So now you're going to hear about the launch vehicle, the big, chest-thumping, booming, heavy-lift Atlas V, insanely bright, and it's going to be awesome. Rex Englehart's here to talk to us about it. He is Kennedy Space Center's Launch Services Program, mission manager here at KSC, where he leads the mission integration teams that are responsible for managing all the integration and launch vehicle engineering aspects related to these assigned missions. So with that, Rex, please. Rex Engelhart.
Hello. First off, I want to thank you guys for being here. Anybody that gets the word out to the people about what we're doing and gets them excited, I like it. And I appreciate it. My name is Rex Engelhart. As he mentioned, I'm one of the mission managers for the Launch Services Program. I've been doing that for a little better than 10 years now, and it's a fun job, I can tell you what. We start with rockets, with spacecraft, back before they're selected. In my office as a mission manager, we get involved with, NASA's got a process of selecting satellites to go do things and selecting teams to go build their spacecraft. And we help pick out their launch vehicle requirements and help them with a review of the proposals. And somebody out of that process, after 2 or 3 years, gets selected, given a whole bunch of money to go build it. And that's where I go introduce myself to them directly. And then we go through the process of kind of holding their hand through the process of seeing what their requirements are, doing trade studies, looking at the different rockets that we have in the stable of available rockets in the commercial market that America has. We select one, and then we buy it, go to the rocket store and pick one up. And then we spend about 2 or 3 years integrating it. It's normally 30 months. And we integrate that satellite onto the rocket. My job is to lead a team called a mission integration team. And I'm the lead of that team. And we kind of hold their hands, and we try to bring experience from other satellites and other programs and make sure that satellite fits on that selected rocket and that they work well together. You got vibrations, you got acoustics, you got electrical connections, you got mechanical connections, you've got sequencing, you've got all kinds of things that have to be addressed and looked at over the course of that 30 months to make sure that satellite and the rocket as a system work completely and work well. And that's my job. And I've been doing, like I said, for about 10 years. I don't know if you guys, how long you've been following this stuff. I started with HEDI 2, and I'd be back in the 99 time frame, probably launched out of Kwajalein Island. I've done MAP, which looked at the universal temperatures, look at the heat signatures. I've worked with ICESat, ChipSat, which are 2 spacecraft that launched. I've worked with the SDO that launched just a few months ago, about a year ago, I guess now, looking at the sun. I've worked with Stereo, which is a pair of spacecraft looking at the sun. It's an exciting job. It's just a lot of fun. Our involvement is not only just the mechanical, the integration of the satellite onto the rocket, but when the satellite is built at the factory, they ship it down here, and part of my team provides them with a facility to process that spacecraft in, and kind of holds our hands. We find out, do you need forklifts? Do you need trucks? Do you need alcohol? Do you need all the different chemicals and processes they need? We make sure we get everything provided for them, and then we take them out. We take them all the way out they get encapsulated and taken out to the pad, and then they get launched. And we have my group, the Launch Services Program, has a launch team that actually launches. So it's cradle to grave, about 4 to 5 years. And that's a real quick summary of what my job is. We think of ourselves in the Launch Services Program as Earth's bridge to space. We're providing that bridge that gets the spacecraft where they're built in their home environment down here up into space, and if they're just going to stay in orbit around the Earth, that's the end of that's where they're going to stay and do their job. Or as MSL's doing, is heading off to another place like Mars. So that's kind of a quick summary of my job. I got so little time to talk to you guys. I always like to leave time for questions. It's one thing I like today. I've seen lots of opportunities for questions and answers. But I'm a little bit more of the homegrown variety of things. So I know you guys have been doing some touring. You've been going to the visitor center. You've been learning about rockets, maybe following them for years if you've been interested in it. Do you have any questions about how to do this process? How do you make a satellite fit onto a rocket? How do you buy one? Just anything you want to ask, I'm here.
Question to your right.
Hi there. I've got a
question around when a rocket leaves Earth, especially to go sort of into the solar system, about how do you avoid satellites and the International Space Station? Do you have trackers, or is it potluck? Or how do you make sure that it's not going to crash in the upper atmosphere? Always just being curious.
Well, you know what? That's a good question. And it's actually one that's been evolving. The answer to that has been evolving over the last few years. Bottom line, potluck. But the satellites, when you get up that far away, moving that fast, and things moving in kind of orbits that aren't, they're not just. If everything was, quiet, they kind of stay in one place. But you got solar winds, you got other things that are affecting the Earth. You got mountains, you got a little bit more gravity where a mountain is. There's all kinds of things that are, adjusting the orbit slightly. So knowing exactly where those things are is almost impossible. We went into that process and said, let's take a shot at it. So we went in and took a look at satellites and especially manned objects that are up there, but other things that we don't want to hit, and tried to do that and then take that with the accuracy of the rocket going up and how well we can predict where that's going to be and how well we can predict where this different objects are going to be. And we tried to go through that process, but then we went through and did a statistical analysis of how well could we really do that. How well can we really, if you put error bars on how accurate we know where things are, both the rocket and the other things up there, and you weren't buying much. That basically boils down to it's a great big space and a little bitty spacecraft. And so there's just, you really can't predict. We're very careful with manned objects, the space station and things like that, and we look at those things. But once you get the satellites and stuff, there's not a lot of benefit. And when you limit your launch opportunity, the only thing you can do is just not launch. We're not going to launch for 5 seconds while that goes over or whatever. When you do that, you may be giving up the only chance you had. So there's a cost. I'm not talking money, but you might lose your opportunity, especially when you've got a mission that's got a limited window. So, another question.
Right here in the back.
What's the difference in terms of energy spent between launching today and tomorrow?
To be honest, I don't know the answer to that.
Is this like a lot of more fuel you need to use, or just pretty much the same?
Well, the rocket only holds so much fuel. So it's more a matter of targeting and whether we've got enough energy within that rocket to get it in the proper trajectory that it needs to get, in this case, to Mars. And there's a window where you got Mars is kind of moving around this way, and the Earth is over here, and we're kind of going to cut across the corner and try to meet it as it comes by. So you kind of head up to a spot. And there's only enough performance in that rocket. It's mostly, you're not carrying any more fuel today or tomorrow. You're going to it's more where you target and what time you launch it to get it on that path. And I think there's 2 weeks every 2 years that we can launch to Mars. That's the capability of unless you put that's with the mass of the spacecraft. If you use the same rocket and put a smaller spacecraft on it, you'd have a little bit more energy to try and make up the difference a little bit faster maybe or something.
One more in the back, right?
I wondered if you could walk us through what was going to happen, the stages, what we're going to see, and what will you be looking at and what will you be thinking? Will you be afraid? Will you be excited?
I don't know if I'll be afraid. You're always a little sad to see him go, but in a way also, you've been putting in so much time, you're always kind of glad to see him go too. The Atlas V, this is called an Atlas V 541, which means it's a 5-meter fairing. The fairing that the spacecraft sits in is 5 meters. And the 4 for the 541 means it's got 4 solid motors and then 1 Centaur engine. And that's the second stage of the Atlas is called Centaur. So what you're going to see the Atlas is going to fire off its main engines and the solids. It's going to lift off the pad. And it's going to travel up, I don't know the exact timelines, but for a couple of minutes usually. And that's the first stage will burn and arc its way over, head down the right path. And then those engines the solid motors will burn out first. And then the main liquid fueled engines will keep burning. And then that will eventually all burn out. And that engine that stage will be spent. You drop the first stage off. You'll drop what's called the inner stage because the second stage has engines that hang down. And so where those engines are hanging down, you don't want to crush them with the first stage when you're pushing up that hard. So they call it the inner stage. It just transfers the load up through the skin of this ring and then the engines are inside it, so it just protects those engines. So it'll drop the first stage, it'll drop the inner stage, and then the Centaur will light up, and off it goes. I don't know the particulars of this specific trajectory, how many restarts they've got. You've got the ability to restart the Centaur multiple times. It just depends on. I'm not actually working MSL. That's Wanda Harding, and I hope you guys have had a chance to meet her. She's the mission manager for MSL, and she's been working it for several years. And she's the one that's really going to be sweating it when it launches. I'll be at home with my kids watching it, just like you guys. Other questions?
Here to your left.
Are there any plans to build bigger, more powerful rockets so that you can kind of widen that every 2 year window, or go farther, faster?
Is that a leading question? I like that one. That's a good train of thought. NASA's trying to build a bigger rocket. You got the Constellation program. We're trying to get the new big rocket that hopefully put people on, to be able to take people to Mars or to the Moon or some of the asteroid belt. And that's where we're going. We've been turned on to go do that process. They've been working on it for a while, and they're going to go do that. That would be a much bigger rocket. What they're looking at is the Atlas 541 is a very large rocket, but we're talking double or triple that if you start some of the different configurations they're looking at building. And that doesn't only just provide ability to put people to faraway places, and it would open windows up and give you more time. But it also, of course, typically when you have more capability, you tend to put bigger satellites. So those tend to balance back out. It's always a trade-off between that. But you also got the ability to put bigger telescopes. That's an interesting process, is to put, some of the astronomers and stuff are super excited about a really big rocket that can make Hubble look small, put a really big one up there. And it just takes a bigger rocket and bigger fairing to fit them in. Yes?
For my students in New York, how do you know how many stages, and is there a limit to how high you can stack those stages? Do you go wider with it, more solid rocket booster strap-ons? Can you do more than 2-3 stages vertically?
We use multiple stages in the rocket. It's all just kind of an integration. It's a design process. It's a trade study. Some of the rockets, like think a small rocket like the Pegasus, can do multiple stages. It uses more. The Centaur is using, the Atlas is using 2 stages. You got the first stage and you got the second stage, the Centaur. You can think of the solid motors as almost being little stages, because they usually drop off early after a couple of minutes. The first stage is 8-9 minutes, I think, is about where those usually burn. You can put more. The advantage of stages is that you burn them out and you drop them off, and now you're not carrying so much weight. The other thing's changing, but on a liquid rocket, you're burning the fuel, so it's getting lighter as the fuel disappears. And they're burning a lot of fuel. Saturn V, I think each of those engines was draining an Olympic swimming pool every second. There's a lot of mass coming off the rocket. In fact, the liquid rockets, if you watch a Delta IV Heavy launch sometime, it's all liquids. There's no solids on it. And that one almost seems to hang in the air. And really what it's doing is it's losing fuel. It's losing mass. And so as it kind of barely picks itself up, and then as the mass drops, you start seeing it accelerate away. And the old Saturn V used to do that. They spin it up, and it was just that mass falls out. So staging is more a function of what you're using and how you're trying to do it. The Pegasus is a small rocket, but it's got like 4 stages sometimes, depending on your configuration. You just keep dropping little ones, solid motors off as it works its way up. So it's more, if you try to go to single-staged orbit, it gets very complex. It gets very difficult to get a payload on top, and not just because you're carrying that structure that encapsulated that fuel. You've got to carry that all the way up, so you can't get rid of it. So it's just more of an integrated design problem than it is. There's no limit, really. You could put as many as you want, but it wouldn't be very efficient, probably.
I hate to do it. We only have time for one last quick question, so we have to turn over NASA TV to a press conference, so we'll make this last one.
Can you give us any more information about what caused the launch delay from today till tomorrow, and what you did to fix that, and what those things impacted?
I'm trying to remember what that issue was. I read about it. Sorry, what? Yes, they had a battery that went bad. That's what it was. And they got another battery. I'm not sure exactly what technology batteries they're using, but when you're dealing with a flight termination, that's your safety system that blows the rocket up if you have an issue on the way up. So it's very critical. You don't play with that. Just not even knowing the details, probably would have been fine, but you don't take any chances. If you see a little blip, you see a glitch, it's thousandths of a volt too low. What you said, you got to bracket what this is okay and that's not. and it was in that bracket, and they changed it out. So.
Let's give it up for Rex Engelhardt, everybody. Thank you for joining us.
I'll be around if anyone's got any questions.
If you didn't hear, Rex just said he'll be around if you have any more questions. He'll be here in the tent with us. So that's going to do it for the televised portion of today's Curiosity Tweet Up. If the tweets would stay in the tent just for a couple minutes, we'll have a few quick announcements about lunch and tours and whatnot. For those of you joining us online, be sure to watch tomorrow morning at 10:02 a.m. on NASA TV at www.nasa.gov/ntv. A reminder, you can connect with us. You can find all of our various social media sites and properties at nasa.gov/connect, and you can join the conversation here with We Tweeps as we watch the launch at twitter.com/NASA tweetup. So thank you very much for joining us, and go Curiosity.